intelligence. We're looking forward to what is a program 90 minutes of presentation to you today. In a moment, I will present a program for the rest of the morning, but I should introduce ourselves by saying that Minerva is a knowledge engineering company based in Vancouver. We deliver the benefits of artificial intelligence technology to industries dependent on reasoning with complex technical and scientific data. Our technology is built on human semantics, combines machine intelligence with human intelligence to reach conclusions faster, we think, than is possible by humans alone, together with the explanations needed for trust in the results. So our agenda for this morning is I will just introduce a couple of subjects and then hand over to Professor David Poole, who is our Chief Software Architect, a professor at University of British Columbia. David and I have been working together on these things for the last 20 years. After that, I will speak for about half an hour on first on AI semantics and semantics, on our perspective on Inspire semantics, and then a little bit about the vision we have anyway for Inspire and AI. Will then be followed by a practical example of leveraging Inspire's framework in an AI application by Dr. Geological, the head of our natural hazards section. And we're fortunate to be joined thereafter by Matt Harrison, who is now with the BRGM, ex-British Geological Survey, who will talk about the kind of global implications of what's happening in Inspire and interoperability with other global initiatives. And then we'll close off, hopefully, with some time for some questions. So to launch into a quick introduction, there are many types of AI. We're a knowledge representation company and we use semantic networks, and there are many different use cases for reasoning about concepts and instances. So a quick layout of at least 6 or 7 of the types or classes of artificial intelligence. We'll return to this diagram in a few minutes, but we just want to make clear that artificial intelligence is not the same as machine learning. Machine learning is part of artificial intelligence. So a few words about machine learning. Obviously, there is supervised and unsupervised machine learning. Both of them are currently enjoying the limelight, and by currently, I mean for at least the last 10 years. But as time passes, those of us who are really interested in the semantics of knowledge look at papers like this, which are written by up to 20 or 30 authors, expanding on the undoubted power of machine learning, but paying very little attention to the concepts that are being spoken about and reasoned about within machine learning, but without really being defined, and the results being returned to human beings as numbers rather than explainable in human terms results. So this is a nice example in my field, in mineral exploration, machine learning applied to complex ore bodies. One diagram like this, and we'll have up to 29 or 30 concepts, and nowhere in the paper will the authors deal with how the machine learning outputs are translated to human understandable terms. So it's not only us who look at these challenges to artificial intelligence. Late last year, a very readable book called titled Rebooting AI was published by Gary Marcus and Ernest Davis. I think one of the underlying themes of that book, which is really worth a read, is that machine learning needs semantics to explain itself. Machine learning, as David will talk about just now, or AI, needs an awful lot of Bayesian statistics as well, because so many of the answers to the problems we address are statistical in nature. And we're in the process of releasing a sort of second order reasoning engine in our software that is 100% Bayesian based and pays explicit attention to the diagnosticity of properties and their values in models that we use to solve problems. So this is really a presentation about knowledge representation and cognitive AI. There are very large volumes of human learning that are well documented in scientific papers and ontologies and taxonomies. And those are the things we focus on working with. And we find the structures most easy or most utilitarian to work with are semantic networks. We see 4 semantic networks on the right describing 4 different mineral deposits. And as I've just said, we feel it's very important that intelligent systems can explain their results. It's all about explainable AI, and later today you'll see in Geo's presentation how that works. The explainability or the explanations given by intelligent programs need to be indexed directly back into the scientific literature and right back into the papers that they quote. And obviously, the more similar language both the papers and the AI applications are using, the better. David and I later will be talking about the difference between instances and models. The way this finds expression in our software is that instances have properties that have values, and those values are explicitly either true or false, or present or absent. However, when one's talking about conceptual models or concepts, one uses exactly the same vocabulary, except that the attributes and their values, or the properties and their values, are not simply true or false, but they are associated with a probability, sometimes, always, rarely, never, usually, and that's that's where the statistics enter the picture. I think David may say a few words about how prior probabilities, the Bayesian type, included in the mix, make the reasoning even more accurate. So with that, I should hand over to David.
Right. Hi all, greetings from Vancouver, early in the morning here. All right, let's try and sharing my contents. Screen, this. Can you hear me?
Yes.
Yes.
All right, good. Thank you. And can you see my screen?
Yes.
All right, perfect. Thank you. So what I'm going to do is the overall big picture view of what we're doing, and then I'll let other people talk about the details and the applications of what we're doing. So what Clinton and I started off with about 20 years ago was this idea of reasoning about the world in sort of in a big world point of way. So we had observations of the world, and geology were very complicated, but we still want to make decisions about using probabilities. That's what I'm going to talk about. All right, so here's what I'm going to talk about: the motivation. I'm going to then talk about data, ontologies, data, and hypotheses, and then we're going to present this view of ours, which we call semantic science. It's an overarching view of what we're going to do, and then later on, people will get and talk about the details of this. Right. So artificial intelligence is what I do. I'm a researcher in artificial intelligence, and I write books and things like that on it. So AI studies what agents should do. And one of the theses of it is agents acting is gambling. We're talking about what you're doing, acting is gambling, and there's a whole lot of results that basically show as agents who don't use probabilities will lose those who do. So if you're gambling and you're betting and you use probability, you're not. If you don't use probability, then you're going to lose. There's a whole lot of results that do that. And what we want to do is to make predictions, but use evidence-based hypotheses, and we always want to use the best data for doing that. So here's an example of sort of a natural example. Consider predicting the effect of a treatment on a particular patient in a general practitioner's office. Information is heterogeneous. There's lots of different information from all sorts of things. Everyone's electronic health records are all different and unique. And it's often provided because it's unusual. It's not sampled at random. So a lot of the assumptions that people make in statistics are just not true. It's at multiple levels of abstraction in terms of more general or less general terms. Like, for example, just a virus versus a very specific type of virus, like COVID-19, or multiple levels of detail. For example, talking about your leg or a particular part of your leg. So we can talk about it both in terms of abstraction and detail. And the first thing to do is that no prediction is certain. If we're making predictions, you should never believe anyone who gives definitive predictions. If someone tells you you will be run over tomorrow, you should not believe them, because then you'll probably just stay inside and not do anything. If they tell you you will not be run over by a car tomorrow, then you should also not believe them, because you'll probably be reckless and act for it, and act and get run over. So it's important not to believe definitive predictions of people who say this is going to happen. It's much better to have predictions that are probabilistic, because then you can use that for decision making. All right. Here's an example in medicine. So PubMed is where people publish research papers in medicine. It contains over 24 million citations for the biomedical literature, and there are 10,000 papers added each week. And that's an enormous number of papers. No one can keep up with even a tiny proportion of what's going on in medicine. So IBM's Watson and lots of others have proposed to read the literature to provide evidence-based advice for specific patients, and there are quite a few companies that are doing that. What we're looking at is, the question is, can we do better than start with data? So the researchers start with data, they create hypotheses, and then they write research papers from which IBM's Watsons read, or if you actually ask the practitioners, they misread, and then it goes into clinical practice. So thinking about doing this, can we do better than this? And the idea is, we can answer the question, wouldn't it be better to have research published in machine readable form? And that's what we're going to look at here. So we're going to have sort of research, we can get the best research published in machine readable form. We're going to apply everywhere to make predictions. So in geology, geologists know they need to make decisions under uncertainty. If you're asking people who do minerals exploration, there's huge amounts of uncertainty. The success rate's very low. If you're doing most other things, people don't know whether there's going to be a landslide in the next day or the next week. They just know there's a probability they need to act under those probabilities. They know they need to make decisions under uncertainty. Geologists also know they need to use ontologies, because when you build geological maps, they don't match at political boundaries, and there's something wrong there, because the geology doesn't change at political boundaries, but so we need to make sure that across political boundaries we have agreed on vocabulary, so that the geologist maps, so that everything maps. So the geological observations are published by geological surveys of countries and states and provinces and globally, and these are sort of observations that we're going to use in our just like in medicine, we're using electronic health records. Here we're going to use lots of observations about the world that have been published. Geological hypotheses are published in research journals, and we've trying to build systems for minerals exploration and landslide prediction. So we've represented the hypotheses of hundreds of research papers and matched them with thousands of descriptions of interesting places. That's what we're trying to do. We're trying to do probabilistic reasoning, where we observe parts of the world, we make predictions so that we can then use them for action. And here's the picture I'm going to draw. So we're going to start off here with ontologies. Ontologies represent the meaning of symbols, and then we have observational data, which describes the world. It uses the symbols defined in the ontology. So this needs both the data, requires both the world and the vocabulary using. From that, we're going to build hypotheses that make predictions on the data, and then the data is used to evaluate hypotheses. If you do machine learning, you should be familiar with this. There's the training data, and then we build up a model for that, and then we have new cases, and from that we can build then we can build more models and predictions. And all of these evolve in time, and this is what we're going to try to do here, where we might have hypotheses from the research literature, but we can also have machine learned hypotheses. Okay, so here's the outline for the rest of my talk. So I'm going to talk about ontologies first. All right. So in philosophy, ontology is the study of existence. If you look it up in your dictionary, that's what you'll find. In computer science, an ontology is a formal specification for the meaning of the vocabulary used in an information system. And so what we're trying to do here is a specification of the meaning of the vocabulary. And ontologies are needed so that information sources can interoperate at a semantic level. So different information sources can have the same meaning for the same terms. And that's really all we're going to use. That's really what we need ontologies for in this situation, because we're going to make sure that the hypotheses from research papers match the hypotheses from all the different data sources, and all those data sources all interoperate. So there's some of them are enormous. So for example, SNOMED CT is a medical ontology with 311,000 concepts in multiple languages. It's sort of one of these enormous ones. The geology ontology that we did, that we're using at one stage had 626,000 minerals. There was ontologies for rocks, and there was an ontology for time, and there's lots of other ontologies because that's what we need to build our models. So the idea of an ontology, the idea of this is quite simple. So if you look at this building, some people might say they're condos, and some people might say they're flats. Someone else might say it's an apartment complex. What we're going to do is we're going to agree on a terminology. We're going to say we're all going to agree to use this particular symbol for this type of building, and maybe it's a type of residential building. And that's really what we're doing, is just agreeing on the terminology that we're using. The main components of an ontology are individuals, which are entities in the world, which are not usually specified as part of the ontology. So there wouldn't actually be on that building before wouldn't actually be in your ontology. It's part of your database. And there are classes and sets of individuals, and they're often the sets of everything that would be a building is a class of buildings. And there are properties between individuals and their values. So it turns out that individual property value triples are universal representations of relations. So you can represent everything, all relations, in terms of triples. And that's important to know for a lot of what we're doing. And if you think about, if you have a big relational table, you can just think of it, if you just pick the row and the column and the value, that's actually all you need, the information you need to represent the whole table. So if you might have heard of relational machine learning or probabilistic relational models. So, and we wonder, what are these about? Because isn't all, when we learn machine learning in our first course, we all learn it in terms of relations. So relational models, the values can be meaningless names of individuals. And it's the properties of the named individuals that matters. And the indexes into other terms, that's what's important. Okay, so the next part is data. Real data is messy, as a lot of you know. There are multiple levels of abstraction in higher and lower concepts, multiple levels of detail. We're going to use the vocabulary from lots of ontologies. There are parts of the data that refer to rocks and minerals and top-level ontologies and time and all sorts of other places. And there's rich metadata, and if you're doing the probabilistic reasoning, you need this metadata is important. Who collected each piece of information? Who transcribed the information? And most importantly is, what does the protocol use to collect the data? Was it chosen at random or chosen because it was interesting? What was the controls? What was manipulated when? What sensors were used? What's the reliability and operating range? And then there are errors and forgeries, which you also want to take into account. And so here's an example of an observation about the world. So this is in Veneto, and this is the slope information in Veneto. And so this is one of the pieces of data about which we're going to condition on. So this is the slope information in Veneto. And here is and here's another piece of information that we're also going to use. So this is the geology of in Veneto, and this is sort of gives you sort of the clusters there of the different geology used. And so this is a part of the INSPIRE data set that's published from Veneto. All right, so hypotheses, the other parts are just programs that make predictions on data, and to be useful for decision making, the prediction to be probabilistic. So we have these models that are hypotheses that just make probabilistic predictions. And there's a lot of work now on what are called probabilistic programs. And so here's our prediction model. So here's a prediction. Here's the output of this, which is a prediction of soil slides in Veneto, in the same area that we did before. So we're conditioning on the other piece of information, and here's our prediction, the output of this, which can be used for decisions. So one of the things I should mention is how we can reconcile the random variables of probability theory and the individuals, classes, and properties of modern ontologies. So first of all, you need to know that a property is functional means that for every x, there's a unique y that's related to it. So if x is related to y1 and x is related to y2, then they must be the same. So each x is unique. So for now, for functional properties, there's a random variable for each individual property pair. We can actually have that as a random variable. It only has a unique value, and we have a probability distribution of it. So the range of the random variable is the range of the property. So if height is functional, then a building has a unique height. So building 17 height can be a random variable, which we can be unsure about. For non-functional properties, what we're going to do is for each individual property value triple, we're going to have a Boolean random variable. So if the year restored for a building is non-functional, then the building restored 1988 could be a Boolean random variable. Okay, so there's actually a nice matching between random variables and triples. So the semantic science we're going to do is going to be based on the fact that governments are publishing data with rich ontologies, and the journals are also forcing people to publish data. So there's lots more data that's available for people to do. And the idea is we're also going to publish hypotheses that make probabilistic predictions about this. And so the sort of problems we're going to do is, given a model, find the most likely instance given the model. So for example, what location most likely has cobalt? Which people are most likely to have cobalt-19? So we're given a model of cobalt-19, COVID-19 or cobalt, and we'd like to find out the most likely instances. Given an instance, find the most likely models. What minerals might be on my plot of land, if you have a plot of land, or if you have a patient in a doctor's office, what's wrong with this patient you might want to be interested in. We also have instance-to-instance matching. What other plot of land is most like this one? What other patients are like this one? And model-to-model matching. What other model is like my COVID-19 model? We might have other models about diseases. And this is often not a big data problem. So for all the mineral resources put together, there are less than 10,000 known high-grade deposits. And that's not very many from a machine learning point of view. And with 100,000 clinical findings in SNOMED CT for almost every pair of diseases or symptoms, there's no one in the world with that pair of diseases or pair of symptoms. So you can't learn it from data because there's basically no one. You need to sort of learn how the world works in order to do this. And these models are typically complex causal models built modularly, and you can't construct causal model from observational data alone. There's not enough information in there. And if your hammer requires millions of examples, they're just not applicable for a lot of these cases. So we need something more than just sort of something that requires big data. So in conclusion, we started off thinking about semantic science, the way to develop and deploy knowledge about how the world works. Those scientists and others develop models, refer to standardized ontologies to make predictions for new cases. And we want to deploy these models all over the world. Whenever we have data in the right format, we can then display that. We can use that data. Okay, I think my time's up. So does anyone have any quick questions? Does anyone have any questions? All right, it's over to you then, Clinton.
Okay, David, can you hear me?
Yep.
Yeah, I think we'll, there aren't any now. We'll certainly take questions at the end. So I will now share my screen. Share content. Okay, confirm, can you hear me, David?
Yes, I can hear you.
Okay, thanks. So, well, if there's one message in the next 25 minutes that I'm going to try and deliver, and that it is that Inspire provides perhaps the best, or not perhaps, exactly the infrastructure that we need for applying the kind of artificial intelligence that David's just been talking about. It's unparalleled in the world for the kind of infrastructure surrounding semantics and standards for semantics and support for those standards. It's unparalleled. There are similar examples. Maybe one can think of EarthCube in the United States, but none of them is as expensive as Inspire. So these are the headings that I'll be talking under right now, but rather than stick with this summary, I'll just go straight to my slides. Oh, I should be on full screen. So some definitions first, which I won't spend time on, but they need to be up there. Artificial intelligence we view as the capability of a machine to imitate intelligent human behavior. Intelligence is the ability to learn or understand and apply knowledge. Knowledge is the fact or the condition of being aware of something and or its meaning. Meaning is what is expressed by a word, text, concept, or action. Semantics is the study of meaning. And language is a systematic means of communicating by the use of standardized signs, sounds, gestures, or words, having understood meanings. Can you see my screen?
Yes, we can see.
Yeah. Okay. My interface doesn't show the control interface anymore. Okay. So the conclusion is that AI needs language to communicate with human beings. Linguistics is the study of language, and there are a number of different levels of linguistics, starting right down at the sounds we make and going up to phonemes, words, phrases, and sentences, and then the literal meaning of phrases and what they may mean changes. In the context of this webinar, the three most important levels are obviously words, which correspond directly with the Inspire code lists. An example of a code list value is a granite. It's a certain kind of rock, and it's well defined by Inspire. Phrases and sentences, we now introduce really the concept of syntax, how these words relate to each other in structures like sentences, or as David spoke about, like triples. So we have a triple here, polygon 1336 has bedrock granite. That's a triple subject, predicate, object. And then obviously we're concerned about the meanings of those phrases. That this phrase up here means that the bedrock in the area of polygon 1335 has been determined, and it has been shown to be an igneous rock. The reason I put in igneous rock here is that because of the semantics defined by Inspire, we actually know that if something is a granite, it must be an igneous rock. So what we then need to deal with respect to the fact that an awful lot of the information we have at the moment in Inspire are in relational database tables attached to points, lines, or polygons. And yet I keep saying that in our field of AI, we work with triples, RDF, Resource Definition Framework, or semantic networks. There have been tools around for a long time that relatively easily convert tabular information to graph information. And we don't have time in this presentation to go into them, but they are there and they've been there for a while. So it's not a big problem converting from relational databases to semantic networks. At the same time, the syntax, a lot of the syntax and some of the semantics in Inspire are provided in the UML diagrams that lay out the relationships of different tables to geometric objects and so on. Turns out there are many tools out there for the conversion of or transformation of UML diagrams to ontologies. Again, we don't have time in this presentation to go into them, but here are a couple of academic presentations on the subject. A tool that we use quite often is provided by Top Quadrant as a commercial tool. So there are no great hindrances to converting relational database data and that's in Inspire and the knowledge frameworks that are in UML into ontologies. Returning now to our diagram of the different classes of artificial intelligence, we would just make the case that really the answer is not going to be only in semantic systems or only in machine learning systems. They integrate well together, particularly if one thinks of machine learning as often being considered really as a perception type of system, something that can do in seconds what human beings can do in seconds as well, such as facial recognition and extraction of patterns from magnetic airborne magnetic surveys, whereas the cognitive side of things, cognitive systems, take human beings a finite amount of time to think about and come up with answers. And very often in hybrid AI systems, we find the outputs from machine learning as providing very useful inputs to cognitive systems that we can reason about. So I think if you read the book I recommended earlier, the recommendation there is that hybrid systems are going to be the answer in the longer term for AI. What we also have to deal with in thinking about knowledge processing and intelligent systems is communication. And there are three kinds of communication we have to be concerned about. Communication between people first, and if we don't understand and get that right, we're not really going to get right communication between machines and between machines and people. So as this slide sets out to explain that many specialists in science at the moment are aware that as they specialize, they develop language that isolates them from their co-researchers. And we have this problem in mining, where metallurgists aren't speaking the same language as geologists, who are not speaking the same language as the environmentalists they have to work with. So, you know, semantic solutions are the ones that are important here because they make explicit what we mean by our words, and they make them available to interdisciplinary groups to work with. Of course, it's not just human-to-human communication we have to worry about, it's machine-to-machine communication. And that was highlighted early in the 21st century by Tim Berners-Lee and his vision for the semantic web. Some people think this is a dated version of the world. I don't, and there are lots of people that don't. This diagram of the semantic stack, starting down here with Unicode and URIs, and eventually ending at the top in trust, has been rejigged by many people, but it still bears, it's still a very useful framework to design to today. His vision was of the semantic web of machines being able to talk to each other, which depended, of course, on defining the words with taxonomies and ontologies. Now, when we get onto the vexed subject of how we can communicate with computers, it highlights the fact that we're very inconsistent in the way that we communicate with ourselves. But human brains can take that into account in real time pretty easily by just saying, can you repeat that, or tell me what you mean by that word, and so on. Machines can't do that, so we have to be very explicit with machines about the words we use. The challenge is sort of well represented by the fact that in my period of 30 or 40 years as a geologist, I've had to work with at least 5 different taxonomies of rocks, and it was grappling with these different taxonomies over a period of 3 or 4 years that the group behind the One Geology site that Matt may mention later today grappled with this to come up with a single sort of overarching taxonomy of rocks, which has now found a home in Inspire. And I think there are many different taxonomies that Inspire uses that need the discipline that was attached to coming up with one coherent Aristotelian, we'll talk about that just now, taxonomy for rocks. And this discipline needs to be applied to all the taxonomies that are in Inspire. So really the concept we're talking about, or in the vision for Inspire as a framework for artificial intelligence, is that we can use the words, the actual code words that are in the code, the words that are in the code list of Inspire to do the computing upon. We reason with the very words that are in the data columns of your objects in the maps. And this slide is just trying to represent how that works. If polygon has slope very steep, has road cutting, yes, has current rainfall very heavy, then current rockfall hazard is very high. That is it's a piece of reasoning that can be done with the content inside the data columns of your current maps, but it can only be done if the semantics are absolutely correctly defined. So David's already described what an ontology is. This just presents a graphic that makes it a little clearer. Ontology editors are quite complex beasts. They have the taxonomy, they show the taxonomies to the knowledge engineer, a little bit of metadata about the taxonomies, and importantly, the definitions for the words. And it's from these systems that the user interfaces with the domain experts or with the relational database to RDF transformation software. It's by referencing through these kind of systems that we can move our data into semantic networks like this, this description of a mine. Now, ontologies are built from term lists, and those term lists, many of them are either taxonomies or partonomies. And this is an absolutely fundamental concept to be understood if one's going to be using taxonomies for reasoning. And it's a concept that's not often explained, because these two kinds of hierarchies are often conflated. And so dealing first with the kind of hierarchical relationship on the left, this is called a taxonomy in its strictest definition, and it was first recognized as an important data structure by Aristotle many years ago. And here we have an extract from the rock taxonomy in Inspire at the moment, which says that a volcanic rock is a kind of igneous rock, and a rhyolite is a kind of acid rock, which is a kind of volcanic rock. This is very different from a partonomy, which is also may also be hierarchical, and is explaining what a rock is in terms of its component. So this rock has a mineral, and the mineral has an element. So the element is part of the mineral, and the mineral is part of the rock. And in reasoning systems, it's important to know that some of the properties of, in a kind of relationship, propagate up the hierarchy. So if the mineral has element mercury, then the rock has element mercury. So this attribute has propagated up the hierarchy here, in exactly the opposite direction from which properties propagate within taxonomies. Within taxonomies, they propagate down the hierarchy. So anything we say about anything that is true about a parent class of a gabbro or of a granite is true about the granite. So properties propagate down this hierarchy. If these two are mixed, if they're not distinguished in a code list, you cannot use that code list for intelligent reasoning. This subject is explained in more detail in a book co-authored by David and Professor Alan Mackworth on artificial intelligence, and that book is available free online, and this concept is explained at this reference. This is a slide to highlight the unfortunate fact that one of the most popular, globally most popular terminology editors is called SKOS, Simple Knowledge Organization System. And it's really grown out of library science, where the people needed to know where to put their books to most easily make them found. And the relationship in a SKOS hierarchy, I will not call it a taxonomy, is broader than and narrower than. And if you think about it, that explains why there's this conflation of kind of and part of. It doesn't distinguish between the two, so you end up with kinds of and part of relationships all mixed up. This diagram on the left illustrates how the enhancement of molybdenum, this is a semantic network describing a mineral deposit, and if we've found out that a particular mineral assemblage has enhanced molybdenum in it, this has implications for the zone that it's in, for the host, the rock that hosts that zone, and indeed for the deposit. This has an awful lot of relevance when one is searching through information like this, because if we've entered molybdenum here and not entered it here, and someone's looking for a deposit that has molybdenum, their software either has to search through the semantic network or during knowledge capture, this attribute needs to have been propagated onto all the nodes where it actually belongs. So that's what we're trying to show there. Getting back to the semantic network, I beg your pardon, the semantic stack, it turns out that pretty much each of the components of the semantic stack, as Tim Berners-Lee envisaged it, merits in a cognitive AI system a different piece of software. We found this in Minerva. And so, you know, at the very bottom end, when we're introducing relational databases to RDF format, we have software called DB Converter, brings it in, filtered through an ontology. We need an ontology editor. These are complex things to write, and we use a commercial one called Top Braid. We'll talk about the alternatives later. We use a specialized taxonomy editor that respects the Aristotelian principles for creating our taxonomies. We have our own proprietary reasoner, which can prove that our answers put out by the system are correct. And we have a document management system that is able to use the controlled vocabularies of Inspire to make it easier to search through our documents, and also to use those documents for knowledge entry into the system. So trying to close the gap, if you like, between knowledge expressed on the computer and knowledge expressed in the scientific literature. So let me just check where I am on my time now, 7:43. Yes. Okay, so now a little bit about Inspire semantics themselves. Probably most of the people on the workshop know that Inspire standards cover 34 themes of broad societal importance. This is a very broad scale of standardization of terminology and knowledge models in the UML diagrams. It's unprecedented in scope in the world, I would say. And another way that it's unprecedented is that it's legislated. So I know there are problems in respect of uptake, but let's hope that those problems are overcome, because there is no other way out to build intelligent systems other than standardized language to some extent, and provide the tools to for people to evolve those standards and to add to them in a convenient way. And Inspire provides all of those. So we go on to the next slide. When I say unprecedented, it is nice to think of other examples in the world where government has stepped in and said they want to get involved in semantics. And to some extent, the Canadian government, interestingly, did this about 25 years ago as the result of one of the world's biggest frauds. Some people on the seminar may remember the Bre-X fraud, where claims by this company to the mining industry and the investing general public were that they'd found the biggest gold mine in history in the world, and it was all a big scam. And in order to preserve the status of the mining investment industry in Canada, the Parliament of Canada introduced legislation governing how geologists like myself will write technical reports about newly discovered mineral deposits. That is the National Instrument 43101. You can read about it. They don't actually define the very terms we have to use in the different paragraphs, but that national instrument lays out 24 or 25 different headings that we have to write about when describing a mineral deposit and its economic viability. And I wonder how long it's going to take before certain governments promulgate similar legislation, compelling their scientists, when writing up environmental findings and so on, to use a language that is understandable to the computer, so that the computer can aid the kind of e-science and hypothesis testing that David spoke about earlier. If one scientist is writing up with one set of terminology and another scientist is using another, it's impossible to do the kind of work that David spoke about earlier. So this diagram is simply an illustration for those who don't work closely with these standards in Inspire, how the UML diagram is providing an awful lot of knowledge structure, both in terms of syntax and semantics. This is the high-level geology UML diagram for how geology is implemented in Inspire. And what we see it being explicit about in this part of the diagram is a part of relationship, compositional part of a geological unit. And in this part of the UML diagram, it's being explicit about a kind of relationship, how natural geomorphic features can be parts of geomorphic features, but you can also have anthropogenic geomorphic features as part of a geomorphic feature. It's interesting to note that we're not the only people that have been playing around in this area of converting UML diagrams into ontology and the technology of the semantic web. There are clearly a number of people in Inspire who over the last 5 or 6 years have been publishing on addressing exactly the same challenge. Okay, so drilling down now to some of the more nitty-gritty detail. How does Inspire, how are these semantics presented to the users inside of Inspire? I thought it appropriate just to show that the Inspire website has fairly good navigational system for hunting around the different themes that it addresses and the many different taxonomies and mixed up partonomies that these formalize. And here's just an example of the semantic detail that is in them. Very clear definitions in English and the other languages of the European Union for each of the codes in the code list. So here, Earth surface setting is defined in clear English. So as I've been intimating, some of these code lists have been prepared by people who were aware of this distinction between part of and kind of, and some were not. Fortunately for us working with a lot of the earth science, using a lot of the geological taxonomies in our reasoning, the groups that worked on the GeoSciML standard and in the One Geology environment were aware of this, and we can pretty well use the taxonomies or the code lists in most of the geology specifications as is. This Aristotelian class explorer, the ACE taxonomy editor that Minerva provides from its website as a free-to-use tool, is able to import all of the code lists in Inspire, whether or not they are true Aristotelian taxonomies. And once within the ACE system, and this is the purpose of ACE, one is then in a very strong position to sanitize them, if you like, to re-engineer them and to extract from them, take out from them the part of semantics and put them somewhere else and make them true Aristotelian taxonomies that can be used in reasoning. And here is an example of a common one that there's a fair bit of literature about people struggling to get right, the Hilux land use classification system. It is one of the standards in Inspire. This is an elegant hierarchical diagram that Jake McGregor produced in his workshop on how to use ACE, presented yesterday. And what he was pointing out and what I'm pointing out as well here is that there is a conflation here of kind of relationships with part of relationships. Farming infrastructure is not a kind of agriculture in the same way as agricultural production for own consumption or agricultural production for commercial production is. And if you want to know more about the difficulty of mixing up these relationships, have a look at the recording of Jake's webinar yesterday when it comes out at the end of the virtual Dubrovnik workshop. In the background here, I show some of the workings that some of our staff have engaged in trying to sift out the part of and kind of relationships actually in Hilux. So this is a printout in Excel of the hierarchical arrangement of the Hilux terms with their definitions. And in this case, the knowledge engineer is trying to work out what the subject, predicate, and object is in the sentences describing the term here, so that we can clearly understand which is part of and which is kind of. If one thinks into the future about how AI is going to be important, one of the most important areas is going to be how it combines the law and what we as scientists or environmentalists are seeing in the environment and in our surroundings, especially in the time of climate change. So we can imagine that the link between the science that we represent in our maps and the law, in particular European Union law, is going to be important. And we can envisage a time when our data, just like David explained earlier, once it's in standard terminology, if that terminology is the same as the terminology in the law, then we'll be able to much more easily see where the law is being complied with and when it's not being complied with. Turns out that in the European Union, significant advances have already been made in interfacing case law with ontologies and with carefully selected taxonomies and word lists. And I draw attention to this European Commission finance study over the years 2013 to 15. The study was called EU Cases and has led to the commercially viable product. You can now go to the Euro Cases, closely named, not EU Cases. Now it's called Euro Cases. It's a commercially viable product offered on the internet as a software as a service. It's a unique multilingual informational service providing online access to case law of the leading jurisdictions in Europe related to the application of European law. It's all built on a semantic backend, relying on thesauri and taxonomies. And this, in my view, is an environment, again, that's unparalleled in the world, and all provided by Inspire and Inspire type tools and technology. So if we think of Inspire as an ecosystem for managing semantics, what does it offer? Well, these are just for those that are not familiar with them, these are the areas that it offers entry to the system from the home page. There are learning headings, there are implementation headings, there are participation headings, and guides for users. These facilities and services are all necessary for large-scale deployment of cognitive AI, and we don't see them being deployed quite like this anywhere else in the world. So examples of, just checking my time here, 7:55, I'm okay. Aspects of what Inspire provides with respect to maintaining semantics are, first, a theme community management. So there is a place to go if you need to ask a question or air your grievance about certain semantics that are important to you and that are in the standard. And, you know, there are other groups in the world that have this on more focused groups, and how these groups can interact with those focus groups is a challenge for the future, but you've got to start somewhere. And this is the most integrated, broadest based community management theme area that we're aware of globally. Importantly, each of these theme areas has a nominated person, a human being that's in charge of moderating and curating the semantics that have to do with that theme. And if you hunt around the Inspire website, you'll find that some of the themes are actively seeing contributions, and certainly in one or two of the themes we're interested in, the ones to do with natural hazards like landslides, the discussion groups are reasonably active, and they're certainly talking about important things, as evidenced here. Now, critically important to any standard is, for its adoption, there must be some flexibility to allow the users of that standard to adjust it in one way or another, so that if they have an application that really needs some other semantics, they are not crippled if they don't include the semantics that they need. And incredibly wisely, Inspire provides that facility by allowing for extensions to their standards and a very solid infrastructure for making any extensions that you make evident to other people so that other people can use them. And this provides an evolutionary path for standards to evolve and get better at their core with the passing of time. And there's no doubt that that's going to happen. So anyone who's really interested in AI of the future needs to be interested in how you evolve standards, because language itself moves. Human language moves. So on the Inspire website, the software that actually runs their registry for registering all the code lists and the theme standards is called Registry, but it has a 3 in front of it, RE3, GISTRY. And this is a software system, a web software system that can be set up independently by users who want to be compliant with the Inspire standards on their own servers. And so long as they follow the guidelines provided by Inspire, they can extend the standards in Inspire, serve them in their own registry, and thereby be Inspire compliant. And as you'll hear from Geo later today, Minerva has chosen to do this in the detail with which we address. Landslide has its required more detail than is available in Inspire, and we set up our own Inspire registry. We've followed all their guidelines. Our application is therefore Inspire compliant, and all our terminology and syntax and semantics are available for other people to use. So with respect to the tools available for working with these semantics, it's clear as well that other people in the European Commission were interested in ontologies, because they have funded over time an ontology editor called VocBench, which is now available in its 3rd edition. I'm not sure how many users there are of VocBench in the world, but I felt it important to draw this tool to the attention of the seminar. There are a number of other tools to choose from, such as the open source Protege ontology editor that comes out of Stanford University. Has a bit of a learning curve to it, as does the one we use, which is a commercial ontology editor called Edge. Edge stands for Enterprise Data Governance. It's put out by Top Quadrant. There are many choices that one can make for editing one's own ontologies. And in this environment, I need to come back and emphasize that if you're interested in code lists that can be used in AI reasoning applications, then please take a look at the Aristotelian class editor. There's a fair bit of up-to-date documentation around it on our website and within the Poole and Mackworth text on artificial intelligence. So now just a few words on, I've spoken about AI and semantics, and I've spoken about the semantics within Inspire. Just a few words before I hand over to Geo about Inspire and AI. I think there are at least 3 facts that we can bear in mind now. Standards are required for interoperable data and knowledge. And this interoperability is important at both scientific, legal, and social levels of our society. At the same time, interoperable data and knowledge are required to build scalable AI applications. And the semantics of data used in AI need to be made clear for AI output to be explainable. So if we have a vision, and this in many ways has been the vision of the company Minerva. Ironically, we're not a European Union-based company, But because of all this vision for Inspire, we have established an office in Darmstadt, where we work fairly closely with one of our partners, We Transform, which is also a company that's committed to the future of Inspire. If one believes in these facts, then the vision is that we should leverage the considerable Inspire standards infrastructure to provide the globally scalable AI applications of the future. That's the vision of Inspire and AI. How do we implement AI applications based on Inspire? Well, we need to identify problems that need solving and identify tools and a team structure to solve them. So first, what are some problems that need solving? And David's touched on two of them that we've addressed over the last few years. Where are the mineral deposits? We've built an online AI system which explains its reasoning, that's available for everyone to test and use on our website. It's called Yukon Mineral Targets, and it addresses mineral targeting in the Yukon in northern Canada. We've also built one that Gio's about to show you, which addresses a problem of deciding where are landslides most likely to occur in the Veneto area of Italy. So these are examples of problems that can be solved, that can rely very heavily on Inspire infrastructure and demonstrate to the people who want you to believe in Inspire that there are rewards for those who adopt Inspire standards. There are carrots, not just sticks. A key part of being able to deliver on this vision is identifying the tools and a team structure to solve them. And it needs to be emphasized, I think, that to solve these problems, it's not enough only to have a domain expert. It's actually important to have a knowledge engineer, what we call a knowledge engineer as well. It doesn't have to be a Minerva one, but it's got to be someone who's technically at least interested in semantics. They don't have to have a university semantics training, but they need to be aware of the difference between kind of and part of. They need to know how to use a simplified ontology editor like ACE, and in the best case, they may need to know about how to use Protégé or Edge. We believe that without this kind of team at the core of these applications, they won't be built successfully. And then, of course, they need to surround themselves with the kind of tools that we've developed for ourselves. There are other tools like this out there. In the case of intelligent document storage, we've built something called LEO, which stands for Language Extender and Organizer. But we're aware of others that are out there that are more domain specific than ours. There's one called Climate Tagger, which is developed by a semantic web company with Pool Party for assisting scientists in the climate change area. And then there's one developed by the OBO community called Ocean Best Practices, which deals with the taxonomies and all the terminology for oceanography. So these are the tools that teams like this need to have to deliver actionable results with explanations in truly AI type scenarios. Once you've got those, then you've got to obviously populate the team with people. You have to establish the semantics of the problem, use the Inspire models and code lists where possible, create and register extensions where they are needed, and engage with the theme curators regarding possible revision of data knowledge models and code lists, and then deliver the results. And that's what we're going to see an example of right now. And I think I'm exactly on time. I'm 5 minutes ahead. Yeah, with that, I'd like to hand over to Gio Roberti to tell us about Inspire frameworks for landslide hazards. Thank you.
Joe, you're muted. We see your screen, but you are still muted. You have to unmute, please.
Okay, sorry about that. Can you hear me?
Yes, very well.
Okay. Okay, so I will try to give you a practical application of everything that Clinton and David have been talking about. And this, if you remember the semantic web stack, the top level was an application for a user to use and do something with all of this knowledge, structure, and data. And so this is an application in Veneto, in which we use Inspire as a framework for a landslide susceptibility map. So I will, again, kind of summarize the few concepts that we saw before. Why we use cognitive AI for landslide in this case is that because people from different industry need to communicate information and share results. So usually a geologist would go to the field, produce a worthy report and static maps, and then this report would go to an engineer that needs to design some infrastructure. But he has no geological knowledge nor understanding of the technical worthy report to take real action on it. So geologists and engineers do not share the same vocabulary and standards. So now if we look at the picture, we see that the highway was taken off by a landslide last November in Italy. And so there was the landslide took off the column of the highway that was sitting right in the creek. So there was a gap in knowledge transfer between the geologist and the engineer, because the engineer should have been able to know that the column of the highway should never sit in a creek, because landslide go down creeks. And so then there was a lack of knowledge transfer because of lack of standards. Then another issue is the few data problem and the quality data problem that David talked about. So in geology, again, people describe rocks using different words, and there are not enough mineral deposit, or landslide databases are inaccurate or not even there to make prediction about landslides. So then you cannot work with statistical methods in a data-starved environment of which you don't know the data quality. And so then most of geological decision rely still on expert judgment. So the geologists go to the field, look at the slope, and provide an assessment. So we try to improve this expert judgment, taking standardized data and providing assessment based on standards and explainable assessment. So how do we bridge the semantic gap that we talked about between, for example, engineer and geologist, and how do we put domain experts into the computer to make informed decision? And the answer is with standards and cognitive AI. And the standards are, in this case, the Inspire standards we have been talking about for the whole morning. So now, how do we mimic this human expert reasoning into the computer? I would like you to imagine your dream house. You want to buy a house, so you will create a conceptual image of what your dream house might look like. There might be some number of new rooms will be located in some place, and so on. And then when you want to actually buy the house, you compare your real houses in the house listing with the conceptual house in your mind. So now we do the same thing, but we look for landslide. So in this case, we look for my soil slide, dream soil slide, and then we describe it with a set of properties and property values. So this bubble and the arrow and the smaller bubble is what David was calling before a triple. So we have an entity, the sliding soil, a property, a surficial material, and a property value, colluvium. And so we describe in a semantic network with words coming from ontologies, different domain of knowledge, in this case, landslide. So then to each property, there's a specific property value, in this case, colluvium, erosional process, forest. And then on the other side, we have a real world instance, which in this case is a map polygon, a real slope in the world. And this instance, this map polygon, is also described with triples, with properties that are the same that we use to describe models. So surficial material, geomorphic process, land cover, and property values, colluvium, gully erosion, and foreign semi-natural areas. And now we can have different type of match. So we can have an exact match. We look for colluvium and we find colluvium. And again, here we really show how we use words rather than numbers so that the assessment are more explainable to humans. And then we look for erosional process and I find a gully erosion. So these two concepts are stored in a taxonomy, and a gully erosion is a kind of erosional process. And so by being stored in the same taxonomy, the software knows that it found a kind of exact match. And so the score is awarded. And then it's also possible match. So I'm looking for forest, something specific, and instead I find forest and semi-natural areas. So the software knows the forest is a kind of forest and semi-natural areas. So he says, could be a forest in that semi-natural areas, but I cannot be sure. So now we talked about ontology, taxonomy a lot, and here I want to just show you a very simple representation of the ontology. And so here we describe in a semantic network a small ontology describing an area of the world. We describe this area of the world with some properties, this arrow, that define the relation between erosional process and our area of interest. And then the same way, we define our area with a slope, with a stream order, with surficial form and surficial material, and so on. So then this word, erosional process, etc., terras, colluvium, are actually part of a taxonomy, of a kind of relational classification of things. And so then to build our ontology and to make sure our ontology are interoperable and understandable by everybody, we take as much as possible as terms coming from Inspire code list. And then before going to the map, I just quickly remind the overall vision of Inspire, that is to have interoperable data that, as Clinton said, or David said, geology doesn't stop at the border. It's the same rock across the border. It's just humans, they call the rock in different ways. So the vision is to provide a framework in which everybody can understand everybody else. Data are the same structure, same terminology. Everybody can use this data for effective application. So in our case, as Linton pointed out, Inspire is a very nice initiative, but of course, everything can be improved, right? So in our case, we had to extend the naturally zoned schema. So here we see the UML diagram that Clinton mentioned before. That is in the UML diagram, we describe how the different entities and part of our database interact with each other. So we had to add what we have, these red squares. That is the susceptibility area, is a concept typical of landslide, not so frequent in other hazards, and is the relative spatial likelihood of a landslide occurring. So it tells you that a slope is more likely than the slope next to it to have a landslide at some point, but it doesn't tell you when or how big the landslide will be. So we extended the UML diagram, we extend this knowledge. You can access our extension on GitHub, in the GitHub Minerva Intelligence. And then in the same way, also, we needed words to talk about different kind of landslide, because as of now, the natural hazard code list in Inspire stop at hydrological and geological hazard, but doesn't go down, I mean, in floods and landslide, but doesn't go down to different kind of floods or different kind of landslide. So we extended the landslide classification using this ACE tool that Clinton mentioned before, to build Aristotelian taxonomies that are multi-hierarchical and so on. And here we have the link to our code registry for the code list. I will make sure I got just a message now that the video is not working, and I will make sure we'll update send you the real link later on. Okay, so in a standard workflow, we will gather data aligned to some internal database standard, to some internal semantics, and make intelligent algorithms to provide assessment and recommendation. By using Inspire, databases and semantics should be already all in the same format, and this should allow for more effective artificial intelligence reasoning. To transform data, we have used the WeTransform tool, AStudio and AConnect. So we collect all the data and we align them to Inspire and serve them in the web map through the map service. And both of them are AStudio and AConnect are provided by the company WeTransform. So now I would like you to walk through this web application showing Landslide in Veneto, Italy. And I want to mention that this project won the Inspire Helsinki Data Challenge last fall. And typical use cases are from emergency management to land planning, insurance, and so on. So there's a real application, real use case for this kind of application. Now here you can find the link to the scientific paper under open peer review process by the EGU journal, Natural Hazard Earth System Science. You can go and check it out. And then I would like you to see the map. So I stop sharing this and I will share my, okay. Can you see the
Yes.
web map? Okay, perfect. Okay, so for many of you, you might recognize the Veneto region in Italy. You have Venice down here, you have the Dolomites and the plains. So first thing you can see, you have some colors that go from light blue to orange, red, and purple, indicating likelihood of landslide. So where it's flat, it's not very likely to have landslide. And so then when we zoom in, we can see a classification of the landscape. And we can, first of all, click on the polygon and see what we are talking about, sliding soil. So if I click on sliding soil, I'm going to the Inspire registry. And here you can see the definition of sliding soil. And everybody can see it, and so we can agree on which kind of landslide we are talking about. The distinction in kind of landslide is important because different kind of landslides, some of them are fast, some are slow, some are more frequent, some are more rare. So to manage the hazard and the risk from different landslide, you need to understand of which kind of landslide you are talking about. So then here in the matching attribute, we see which attribute have been used to define the score, to classify this slope. And as you see, there are words that so then is describing different concepts stored in the ontology. And then when you click on Open Match Report, you can see here a tabular view of the bubble graph I was showing you before. So we have in the first column, the model, the conceptual model of a landslide. In the center column, the instance, the real map polygon. And then here you have the type of match. Now you see some words that I didn't show before, usually, sometimes, always, rarely, etc. And these words are used to mimic the human assessment. When we talk, we often use probabilistic term. And so this is done to mimic this human expert reasoning. And then the terms actually are used as a proxy for a score that is a logarithmic scale to give an order of magnitude of confidence in the prediction. So always would say is indicate that you would be really surprised if that wasn't true. And rarely you would be surprised if it was true, for example. So then we can see in the match type, when we click on the match type button, we see an explanation in plain language on how the score was awarded. And so we say, I'm looking for flows in soil. and the map tells me that there's a debris flow. So debris flow is a kind of flow in soil, so the score is fully awarded. And then another possibility, having concept stored in taxonomy ontology, is also to provide an advice in natural language. So in this case, it's kind of a data advice. It tells you to go check if the slope has been logged within 5 to 10 years, because if you cut the tree, the supporting roll of trees decay, so the slope is more likely to fail. The roots of trees rot and the slope becomes unstable. So now let's go back to the map, and we can see another functionality is this class for runout. They show you how far a landslide might go if it was to be if it generated from that polygon. And then we can see how the slope perform against other geohazards. So if I click here, I see now that this slope might also have rock slides, but is more likely to have soil slide. In the same way, clicking here, I go to this match report and tabular view of the matching between model and instance. And then we have also debris flows. In this case, the mapping unit are streams, because debris flows are kind of landslide that occur on channels. And so again, when we click here, we see the attribute, we see the definition, and we see different classes of runout inundation zone. And then it's fully explainable, because by having all the different layers, you can actually open the landslide database and see what's going on. So you see there's an airflow going on there, so many different landslide type. And then you can see, for example, the geology as David show you us a quick snapshot, a preview of this. And again, if I click here, I go in A-Connect, and so I see the mapping between the Veneto database and the Inspire standards. And yeah, with this, I think I can go back to this slide and close my contribution. And yes, feel free to ask me any question, maybe at the end. I'm not sure how much time is left. And thank you.
Okay, Matt, we see your screen.
Am I in presenter mode or in?
Yep.
Yeah, good. Hello, everybody. So my name's Matt Harrison. I'm currently at the BRGM, so that's the French Geological Survey. And I was very fortunate in being the coordinator for the Inspire Natural Risk Zones data specification and technical guidelines. And so that's kind of, I suppose, one of the reasons why I have worked a little with Clinton and his colleagues. And I'm presenting a little bit about the larger family of global geoscience standards and where Inspire fits into that. So if we go on to the first slide, so as I say, there is a large and complex constellation of organizations that are involved in the development and maintenance of standards in the geosciences. And I'll pick on some that have been key to the European Geological Surveys and to underpinning the data specifications for the geological data that is in Inspire. I'm very pleased to see that many of my colleagues from Geological Surveys and other organisations that have been involved in the development of these are online, and so it would be nice to have some conversations later. So one of the key driving forces behind GSIML was the Commission for the Management and Application of Geoscience Information. So that is a group that that works under the International Union of Geosciences, and has been working for more than 10 years now in the development of the data specifications and the vocabularies for GSIML. And about 4 or 5 years ago, they joined together with the Open Geospatial Consortium to actually begin working on that standard as something that was globally recognized. And that is the roots of the code lists that are available for geology in Spire. And so to take that beyond, as GSIML was being completed in the latest form, we developed a domain working group in OGC, a joint domain working group between OGC and CGI, so the Council, the Commission for Geoscience Information, and made that so that it actually looked at more broadly at the geosciences and also talked to other standards organizations, importantly in the oil and gas area, in the mining and underground construction area. I'll talk a little bit about that in a few minutes. And so that was really how that kind of overall, we tried to bring in those overall geoscience groups to be able to facilitate those relationships that that Clinton and David were talking about earlier, to actually be able to navigate between the different scientific domains. So OGC is a fairly sizable organization that maintains and develops standards. It is globally representative and also representative in quite a number of different domains. CGI is a group that is quite broadly representative as well, more specifically in geology. OGC is more specifically in geospatial standards, and again, it covers organizations across the world with many member countries and many member organizations. And one of the reasons that that CGI got together with OGC is this very simplified way of building a standard pile to actually structure data and data services. And so that's around building those data services using standardized language, and then building data structures, standards on top of that, such as GSIML. And so it fitted into the pattern that we were interested in being able to share more broadly. And so that's one of the reasons why the GSIML group migrated into OGC. So as I say, GSIML, the code lists that underpin the Inspire data specification were developed out of the GSIML and GSIML group, both with European members, but also with some of our North American and Australian colleagues. And that was developed over many years, and it is quite a robust standard now. And to many extents, the changes that might be required to the vocabularies are best handled by going to the original source of those things, and those propagate through to recommendations to changing and updating the Inspire code lists where necessary. So and another standard that was built and worked on is Earth Resource ML. So this is has been actually only released fairly recently, and is now supported through a number of different organizations. So there was the Mineral for EU project that completed in 2018 in Europe, the One Geology the One Geology portal, which I'll talk about in a few minutes, and then it is used to exchange minerals related information between states, territory surveys, and the federal survey in Australia as well. I'll talk a little bit more about that. And another group, again, that is under the auspices of CGI, has been working on groundwater ML. That's really been pushed very strongly out of Canada, indeed, but and also BRGM in France. And again, it's been developed and is being worked on and used quite widely. So one of the ways that that standards are developed, well, are moved on and used, is through interoperability experiments. It's kind of one of the formal ways of exposing concepts and ideas in OGC, and so we engaged in an interoperability experiment around boreholes back in 2018, and that actually has gone into the enhancement of some borehole definitions and vocabularies that are being used in one of the big European research infrastructures, EPOS now, and so several million boreholes are being made available from about 6 geological surveys in Europe using the concepts that were developed out of the borehole interoperability experiment. And so all of that work and all of those other organizations are underpinning the maintenance and development of that INSPIRE infrastructure in the geosciences. Now, what I wanted to do next was talk a little bit about some of the ways that they're being leveraged. So some of the areas, the places that you can use and find some of those standards, some of the groups that are actually developing or using them to develop their platforms. So One Geology is a global initiative of mainly geological surveys, and it's become, or it was developed as a flagship platform for testing the standards, for implementing the standards, and for allowing organizations to be able to work together in an interoperable way. And so currently there are about 189 member organizations, of which more than 70 are serving data. And because some countries are serving each other's data, there's about data from about 121 countries. There's some screenshots because I wasn't brave like Geo to run anything live. And so many of the data that are exposed through the One Geology portal actually are either are exposed to using GSIML, or indeed other OGC standards such as WMS, where a country hasn't necessarily been able to encode its data in using GSIML standards right now. And so those technical principles underpin around interoperability, underpin what is shown in and available through the One Geology portal, using a distributed model across the entire globe. And the idea is that it provides a window for organizations to demonstrate their geological mapping, their geological understanding, and the data that they have available. more recently, in Ontology, we started some other projects that went beyond just the exposing of data using standards, and so one of these initiatives was Loop 3D. So this was an implicit modeling project, and so this is 3D geological modeling, and the reason that it was is characterized as a loop is because it was about the flow of data and information through the entire process. So from identifying data through various modeling applications, developing tools to model that data, but then also to feed the understanding that's gained about the geology back into the beginning of the process, so it can be used for other purposes, so the data can be reused. And you can see there that in fact there's quite a number of organizations that have been involved in this, and one of the reasons that it's been associated with Ontology, and one of the reasons that many of those organizations are there, is because actually the whole point about the Loop project, it was to follow this, to try to standardize the modeling process, but to use standard and standardized data as input to the modeling process. And so really that's been the focus of the work of work package 2. So work package 2 is the Geological Event Manager, and that is around trying to build a standardized way for the breadth of knowledge that is available in a geological survey, but in a number of different kinds of organizations, being able to bring that to bear in a 3D modeling project. And so it again, using a standardized approach and using standardized vocabularies, it's enables different groups of scientists to be geoscientists to be able to share their data, to be able to make a better geological model in the end. And so so that's kind of been the focus in the last year, and it goes all the way from that geological event manager process to this one is work package 5, which is around the uncertainty, and so the communication of that through the entire process in a standardized way. As I said, GeoSciML and Earth Resource ML have been used quite heavily by the geological surveys in Australia, and so the Australians have focused on building and serving the vocabulary services, and they have been one of the biggest users of Earth Resource ML for communicating the mineralogical data that they have available, both, as I say, at a state and territory survey, but also a level, but also at a federal level as well. And they also use GeoSciML and to expose their boreholes. And in fact, we've been talking to them more recently about using the new developments that we came up with OGC. And so one of the key elements of in the Australian example is that it's been used, it's been financed and leveraged from a number of different organizations within Australia, and it's kind of been supported at quite a high level. And you may have noticed on the previous slide about the Loop project that in fact actually the Australian Research Council were one of the core funders of that project right now. So those of you who have been involved in Inspire since the very beginning know that they were quite integral to the kickoff of Inspire, and have made various appearances. But the point here is that actually, even in the underpinning elements of GeoSciML and the vocabularies, the Australian contribution has been quite great. And so there are also other new initiatives that are in and around the development, and indeed I and others have been trying to push the standardized approaches. So MacroStrat is a very large National Science Foundation funded project in the United States that takes a slightly different geological approach, but they're now talking about taking their approach elsewhere. And so we've been talking to them about the use of standards and the fact that many other organizations outside America are using different standards, and so those are important. And there's other global initiatives, which such as Deep Time Digital Earth, which is currently mainly funded out of China, but there are discussions ongoing about its development in the United States and in Europe. And so again, none of those data science initiatives are really possible without the use of science, without the use of standards, without the use of there's no point in redeveloping standards. It's about leveraging, and indeed, as Gio was just showing, it's about extending standards where more detail is required than has been available up to now. There were also commercial activities, big commercial activities. So there were a number of different commercial groups, some funded through Jeff Bezos and Bill Gates, that are looking for global data sources to prospect for certain minerals, some of the eye-catching minerals such as cobalt, for example. There have been for many years there have been discussions with an organization or a company that were called Neftex, that are now owned by Halliburton, about using these standardized approaches, leveraging what is available, and indeed contributing to the outcomes. So just a final example. So as I said, there were the purely geoscience focused groups that are developing the vocabularies and the standards. This is a French project where about 13 organizations across France have come together around building in information modeling. So it's something that is slightly at the edge, at the periphery of what we've been talking about so far, but they need geological information, and in fact, as geoscience organizations, we need our data to be available in a form that they can use. And so we've worked with these, and they go as far as Électricité de France, from a geological survey to BRGM, tunneling and mining organizations as well. And it was about actually bringing data together from all of these different all of these different domains, science and engineering domains, in a standardized way, to actually see if it was possible to navigate those standards to do something, to construct some tunnels in Paris, I believe it was. I don't know whether I have French colleagues online who can remind me. And so just this diagram here shows that actually there's those same simple concepts looked at from different standards, and the crosswalks between them, and building those crosswalks between them is kind of important. and those are can be translated into things that concepts that are used in other domains, and the example here is tunneling in the top left of the slide. And those building and information modeling discussions are ongoing, and in fact this is just, there is a new working group in between the geological surveys about actually how we can engage more simply with those more construction oriented organizations, and actually, you know, whether through with common standards such as those around city modeling, whether there is some shared futures that we can have. And the standards aren't confined to the Earth. So there's a couple of conferences and a couple of projects that were actually using GeoSciML, using some of the standards to characterize the geology of Mercury in this case. In fact, I think at EGU last year, I was talking to a lady who was using, actually it was a lady from who was using it looking for standards for Mars, and we were talking about whether GeoSciML might be a useful bridge there. So I've just slightly overrun, and I'm very happy to take any questions. As I say, I have a number of colleagues in the audience as well. So thank you very much.
Clinton, you have again the presenter role.
Well, thank you, Giacomo. I'll just bring up my last slide. I had all these on standby. Sorry, I should have moved them on while I was listening. Okay, well, I think that, thank you very much, Matt. It was a wonderful global perspective, celestial perspective that you gave us. I think we have gone over time, but I think we should just, if there's time for questions, anyone who's still on and would like to ask questions, please go ahead. Otherwise, we'll just wrap everything up by thanking everyone for their attendance and by saying that all the authors are available for follow-up questions offline afterwards. Giacomo, what do you want to do? We are over time a little, but we're the last presentation of the day, so it doesn't matter.
It's up to you, Clinton. I'm here.
Okay, well, I will stand by and see if any questions come in. I think people are free to, can they turn on their audio now, or do they have to do it by texting you?
I think they can do themselves.
Are there any questions? I see a question there. Is there a link available for the Minerva registry? Yes, it's Geo, if you're online, I'm pretty sure it's codes. It's Minerva codes or codes Minerva. There it is. Yeah.
Yeah, I typed them in. Is it? Okay, yeah.
Oh, I see it. It's there for, I think it was Kati who asked it, the question. Any other questions? Gio, you made a comment halfway through your presentation, something about the video going off. Can I just check with Giacomo? Was that the recording of the whole meeting that went down, or was that something only Gio saw?
I think it was just a comment that I misunderstood.
Okay.
Regarding the question, the whole meeting has been recorded and the registration will be available soon.
Yes. Okay. Well, Giacomo, if there are no questions, I last call for questions. Otherwise, I will thank the Commission and the Inspire organization for organizing this virtual conference in place of the unfortunate cancellation of the Dubrovnik meeting. Thank you very much for the efficient way in which you led up to this. Thank you to the attendees for joining us. And thank you very much to my co-presenters. And with that, I think we'll say goodbye. Good evening to you in Europe, and enjoy your day in Canada. Thank you, Giacomo.
It was a pleasure.
Thank you, Clinton.